Hi everyone, my name is Jericho Casabe,
My name is George Barraza.
and our project is going to be on the straight edge and compass construction. So to begin, we wanted to first note that we will assume all the axioms that hold in Euclidean geometry. And one of the first tools we use for the straight edge and compass constructions is a straight edge. And so we can think of a straight edge as a ruler that has no markings and is infinitely long. The differences between a ruler and a straight edge is that a ruler will have a finite length and it will have predetermined lengths on it, like centimeters or inches, and it will have markings on it, while a straight edge doesn't have any of the markings and it can be infinitely long. And we use straight edge, like the tool of a straight edge, to draw line segments between 2 points or to extend any existing line segment.
The next tool that we're going to use in this construction is a compass. However, before we get into the definition of a compass, we first want to go over the definition of a circle because that's what our compass is going to be used for. So we got this definition from Oscar. A circle is a set of all points on the plane that are the same distance, which would be the radius away from the center of the circle, which will be O. And as our notation, we're going to use this here with the CE parentheses O for the center point of our circle and R for the length of the radius of our circle. Okay, now we're going to get into the definition of a compass. A compass is an infinitely large radius without markings on it. And we're going to use this tool to help us construct circular arcs or circles in general, where we're going to place one point of the compass on the middle of the circle, and the outer point is going to be used to draw our arcs or circles.
So before we go into the definition of a constructible number, we have to kind of introduce some terminology. So first is a commutative ring with unity or with identity. The unity and the identity can be interchangeable, but it's basically an additive abelian group where an additive abelian group is the elements in a group that are associative. They contain the identity element and its inverses for each element, and it commutes within the set. That's where the abelian part comes into play. A commutative ring with unity also is when the operation multiplication is associative and commutative, with the identity element being the traditional one, and the distributive laws hold. The reason why we wanted to introduce this terminology was because we need to define what a field is, and a field is a commutative ring with unity where there exists no zero divisors. So that means all the non-zero elements under an operation don't give us zero. And every element within our ring is invertible. So that means every non-zero element has a multiplicative inverse. So to now build off of those two definitions, we have that a constructible number is going to be a real number if there is a method to construct this number using a line segment and using it with the tool of a compass and a straight edge. And so we're going to denote the set of all constructible numbers as this fancy looking K, where K is a proper subset of the set of real numbers. And we're going to say that K is a field. So we're going to first start off with taking a look at the construction of the number 2. So we can take a straight edge using our 2 points A and B to construct the line segment AB. And then using our compass, we're going to take center point B and a point A that's lying on the circle and draw a circle with it. And we're going to define that the distance between A and B is going to be the length 1. And so we have a unit segment AB. And so we're going to recall that the definition is for a constructible number is that we use a compass and straight edge. So right now we have the first constructible number, which is 1. And then if we use our straight edge again to extend the line BA and get a point that intersects the circle and the line, we get that the distance between AB is also equal to the distance between BC since they are the same radius within the circle. And so we now get that then we now get 1 plus 1 is equal to 2. And so now we have that now we have a constructible number 2, since we used a compass and a straight edge to construct those two.
So now earlier, since we said that K, which is the set of all constructible numbers, is a field, then knowing that it's a field, we know that it's closed under addition, subtraction, multiplication, and division. So for the first bullet point, since it's closed under addition, then we know that 1 plus any other constructible number is also constructible. So for example, we just showed that 1 and 2 are constructible numbers. So then we get that 1 plus 2, which is 3, is also a constructible number. And then using that fact, we also get that 1 plus 3, which equals 4, is also a constructible number. And we can keep repeating this until we get that all natural numbers. The set of all natural numbers are also constructible numbers. And then similarly for the subtraction, for K being closed under subtraction, we get that the absolute value of 1 minus n is constructible for all n that are constructible. So from this second bullet point, we get that z is also, the set of integers is also a subset of the set of constructible numbers. And then for the third and fourth bullet point, using the same idea, we get that the set of rational numbers is also a subset of the constructible numbers because it's closed under multiplication and division. So for our next slides, we're going to show how irrational numbers can also be constructible. But before we get into that, we're first going to show how to construct the perpendicular bisector, because this is going to be needed to show how to construct irrational numbers. So to begin, we're going to use this theorem also given to us by Professor Vega in our Math 161. The theorem states that the perpendicular bisector of the segment AB is a set of points P that are equal distance to A and B. So we're going to use this theorem later, but first we're going to focus on the construction of the perpendicular bisector. So to start, we're going to start with two arbitrary points, A and M, where the distance between A and M can be any constructible number. And then using axiom B2, we're going to extend the line AM and get that the intersection between the line AM and the circle AM is going to be the point B, where AM is equal to MB. And then from here, we're going to construct two other circles, the CAR and CBR, the purple and the orange circles. And as we can see, their intersection points are points P and Q. And so now, since both circles, the purple one and the orange one, have the same radius, and P and Q are both points on both circles, then we have that they are both equal distance to points A and B.
Yes.
So since they're both equal distance from points or P and Q, then we have that P and Q must both lie on the perpendicular bisector of the segment AB. So then we get that the line PQ is actually our perpendicular bisector. So now we're going to get into the construction of the square root of n, where n is a constructible number. You want to go?
Yeah. So to first start off, we have a theorem which states that if we have three distinct points on a circle where there's a line AC, for example, is the diameter, then the angle that we have, which is ABC, is going to be a right angle. So let's recall that there's this theorem, this is Taoist theorem, right?
Yeah.
There's this theorem where if we have a right triangle where the measure of one of the angles is pi over 2, we can take a point that's between two other points and the two lines, so like CD and AB, are perpendicular to each other. Then we can fix these distances to be PQH, for example, and then we have this notation, which is that H squared is equal to PQ.
So here we're going to start with the segment Well, to begin, we know that one is a constructible number and
Mhm.
n is also a constructible number. So we're gonna create these segments using our straight edge and compass. So we're gonna first construct the segment one and then the segment n, since we know both numbers are constructible. And we want them to be on a line, a totally line. So next, we're same thing. We're going to take the perpendicular bisector of the segment AC. So we're going to do this the exact same way as we did the perpendicular bisector a couple slides ago.
Mhm.
And then from here, we're gonna see that the midpoint is M. So using that, we are now going to construct the circle with M being the center and points A and C being points that lie on that circle. So then we get this construction. And then again, we're going to take the perpendicular bisector, but we're going to make sure it goes through the point B.
Mhm.
So we're going to call this perpendicular bisector the line K. And then as we see this perpendicular bisector K intersects our circle with M being the center at the point B. Now using this fact, we're going to create a triangle. And then using the two theorems that Jericho mentioned, we have that since A and C is the diameter of our circle, and points A, D, and C are all points that lie on the circle, then we have that the angle D is a right triangle or is a right angle. So then using this fact, we have that we can use the second theorem, which is Dali's theorem, and we get that the distance from D to B squared is equal to the distance A to B times B to C. And then from here we get that dB is equal to the square root of n, where n is a constructible number. So because we showed this, or earlier, because we said that K is a field, then we also have that it's closed under addition, subtraction, multiplication, and division. So then from that fact, we get that all these numbers must also be constructible. So for example, the square root of m plus m must be constructible for all m and m that are constructible numbers because k is closed under addition. And then similarly for subtraction, multiplication, and division. But for division, we have to ensure that m is a constructible number that is not zero.
Yes, and I also just wanted to highlight that the important idea from the construction of irrational numbers is actually going to be the quotient and the product, because when we see in a couple more slides, we'll see that we assume that there's a constructible number that we have, and it's going to require one of them to be the square root of a certain number. And so we will use these ideas to help elaborate further onto why those specific numbers we know are constructible numbers. So now we're going to go ahead and build further on this idea of constructible numbers by elaborating further on constructible angles. And so the same concept with constructible numbers, we have that an angle is constructible if you can construct it with a compass and a straight edge. So for example, when we had our perpendicular bisector, we showed that we had alpha is equal to 90 degrees, but we didn't further elaborate that this was going to be a constructible angle because we didn't know what a constructible angle was at first. But since we were able to construct this perpendicular bisector using a compass and straight edge and all the distances within it, give us a constructible number, we see that alpha is also given to us to be 90. And so now we have our first constructible angle, which is 90, or in radians pi over 2. And then you want to learn further on pi over 3?
Yeah, so with this construction, we also get an equilateral triangle, which is a triangle
APB?
APB, yes. And we know this is equilateral because the distance AP is the radius of the circle of the purple circle, and the length AB is also the radius of the purple circle. But however, we also know that the orange circle has the same radius, so the distance from B to P is also the same length as the distance from A to P and A to B. So since all side lengths are congruent, we get that, or are equal, and then we get that these angles must also be 60 degrees by definition of an equilateral triangle. So we get that pi over 3 is also a constructible angle. So now we are going to elaborate further on constructible angles. We're going to show how to get more constructible, or how to determine more angles that are constructible. And one way to do this is by constructing the angle bisector of an angle. So again, using Vega's or Oscar's definition from Math 161, we get that an angle bisector of the angle ABC is a ray BD such that D is in the interior of the angle ABC, and the measure of the angle ABD is equal to the measure of the angle DBC. So using a similar construction to our perpendicular bisector, we are going to construct the circle R, where R is the intersection between the circle with M as the center and points A and B being points on the circle. And we're going to construct the circle R with R as the center and points A and B on that circle. So then from here, we get that the point, if we bisect the segment RB, then that will be our angle bisector. So we are now going to take a point with B as a center and R as a point on the circle. And then we're going to get the perpendicular bisector of the segment RB. And as we can see, this is also our angle bisector. So then we get that this angle alpha is 45 degrees, or pi over 4. And since we were able, so now we know that pi over 4 is a constructible angle. So if we wanted to, we can take the perpendicular bisector or the angle bisector again, and then we would get that half of 45 degrees is also constructible. So we would get that 22.5 degrees is constructible, or pi over 8 is a constructible angle. And then we can keep taking the angle bisector, and all those angles will also be constructible angles.
So now with the idea of constructible angles and constructible numbers, we can go ahead and introduce this theorem that we've discovered, which is that if we're given if we have an angle alpha and we know that that angle alpha is constructible, then we also know that if we take the absolute value of cosine of that angle, we get it's a constructible number. And it's the same idea as if we took the reverse, which is that say we know we have a constructible number and we go ahead and take the absolute value of cosine of alpha, then we know that that angle will be constructible. So the first example that we have will be the angle pi over 4. So we denoted this theorem to be called the constructible number angle theorem so that we can cite it multiple times. And so say we have pi over 4 is constructible angle. And so if we take cosine pi over 4, then we get that that's equal to the square root of 2 over 2. And we know that square root of 2 is a constructible number. And we also know that half or one over 2 is a constructible number. And so if we take the product square root of 2 times 1 over 2, we get square root of 2 is square root of 2 over 2 is a constructible number. And so we can confirm that pi over 4 is a constructible angle by the constructible number angle theorem. It's a similar process that we can do with the construction of pi over 6. So we can take that cosine pi over 3 is 1 over 2. And so by the constructible number angle theorem, we know that pi over 3 is a constructible angle. And so if we use the idea that we had with the angle bisector and bisect the angle pi over 3, we get pi over 6. And so in order to verify that pi over 6 is a constructible angle, we can use the constructible number angle theorem and take cosine of pi over 6, which gives us square root of 3 over 2. And we just showed that cosine pi over 3 is equal to 1 over 2, which is a constructible number. And so we have square root of 3 times 1/2, 1 over 2, is equal to square root of 3 over 2, and we know both of those are constructible numbers, and so the product of those two numbers will give us also a constructible number. So we have that pi over 6 is indeed a constructible angle. So now we're going to go ahead and explore a non-example, which is trisecting an angle, and how trisecting an angle does not give us constructible angles, even if we started off with a constructible angle. So we have this theorem which states that if a number is constructible, then its minimal polynomial over Q has a degree, a power of 2. Before we continue with our non-example, I wanted to further elaborate on the idea that with our straight edge and compass constructions, we have two tools, a straight edge and a compass. And a straight edge constructs lines and a compass constructs circles, and we're only working in Euclidean geometry. And so using lines and circles, we know that the intersection of two lines gives us 1 point, or no point, no intersection, or an intersection at 1 point. But then we also have that a line, or the intersection of a line and a circle gives us that we can get either an intersection point of 1 or an intersection point of 2. And then when it comes to circles, we have the same idea where we can intersect at 1 point or 2 points, or no points at. And so the reason why we have this theorem is because the intersection of lines and circles is at most 2 points. And so when we go ahead and try to explore like the algebra part of it and looking at polynomials, we need to take note that our roots will be at most 2 or powers of 2, so like 4 and 8 and all that. So the first claim that we have is that we can't construct the angle pi over 9, and that pi over 9 angle comes from trying to trisect the angle pi over 3, which we know is a constructible angle. And so let's just suppose by way of contradiction that we can trisect the angle pi over 3 and see that if we can get the constructible angle pi over 9. So let's trisect the angle pi over 3, and we get an angle theta, which is equal to pi over 9. By using the constructible number angle theorem, we can take cosine pi over 3, which we know is a constructible number, and we can go ahead and take cosine 3 times pi over 9. So the product of the number 3, or the angle 3, times the angle pi over 9. And we get that that's going to be equal to cosine 3 theta. And so by the constructible number angle theorem, since all of these are equal to each other, they're all a constructible number. So then we're going to use the triple identity, or the triple angle identity, and take cosine 3 theta to equate to something on the right-hand side. So for simplicity's sake, we're going to take x to be equal to cosine theta, and then we're going to take cosine 3 theta to be equal to 1 over 2. And so when we rewrite our triple angle identity, we get the following on the right-hand side, which is 1 over 2 is equal to 4x cubed minus 3x. And then we want to get a polynomial that's equal to 0, so then we can go ahead and use the rational root theorem to find any possible roots of this polynomial and to see if we can get a reducible polynomial, because as of right now, we have a cubic equation, and we know that we need some sort of minimal polynomial where the highest degree, which is right here, right now, the leading coefficient has a degree of x cubed. And so we need to have some sort of way of reducing this polynomial to where one of the other polynomials that are reduced, that this polynomial reduces into, is a power of 2, whether that's 2, well, right, I guess in this case, it would need to be 2. So 2 or 1. So the possible roots using the rational root theorem are as follows. And if we try to plug in each possible root, we see that none of those roots will give us 0 at the end of the day. And so we know now by the rational root theorem that this polynomial is irreducible. And so by the theorem that we had introduced, we know that the angle of measure pi over 3 just can't be trisected. That's it. And so we can do another like example to further elaborate on this idea of like using algebra to showcase whether or not like these constructible numbers and angles are constructible. And so we have another one, which is the cube root of 2. So if we take the cube root of 2 and turn it into a polynomial that's equal to 0, we have x cubed minus 2 is equal to 0, and that's a cubic equation. And so by the theorem that we had stated, which is that we needed to have like a constructible if a number is constructible, then we have a minimal polynomial of degree with power 2. But since our cubic equation is irreducible, and we know it's irreducible because if we took the rational root theorem again, we have possible roots which are plus or minus 1 and plus or minus 2, and none of those will give us 0. And so we can't reduce the polynomial any further down. And so we're stuck with the cubic equation, and we know that we need to have a polynomial where the degree is a power of 2 and 3 is just not power of 2. And so we know that this polynomial is irreducible, and we know so is irreducible, and therefore the cube root of 3 or the cube root of 2 is non-constructible.
To add on to that, we know that higher degrees of roots are also non-constructible, but that does not mean that all higher degrees are non-constructible. Because, for example, we can have the cube root of 8, which is equal to, or which is equivalent to the 2. And we know 2 is a constructible number, so the cube root of 8 will also be constructible. So just because it has a minimal polynomial of degree higher than 2 does not entirely imply that the number is non-constructible. Because there is certain cases like the cube root of 8 where it is a constructible number. So now we're going to get into what I believe is the funnest part of our presentation, which is constructing a regular pentagon. Before we get into that, let's kind of go over what a regular pentagon is. So we know a pentagon is a fivegon, which is a polygon with 5 sides. And what makes it regular is the fact that all side lengths have equal length. So that's what a regular pentagon is. It's a pentagon where all side lengths are equal.
And all the interior angles share the same angle.
Mm-hmm. Okay, now we're on GeoGebra. To begin, we're going to be given a line segment or 2 arbitrary points, and then we're going to create a line segment AB
using the straight edge. And then we're going to go ahead and take a compass and take the center point A and a point B on the circle and draw the circle, and then use axiom B2 and our straight edge to go ahead and take the extend the line AB so that there's a point C where this is the intersection point between the line and the circle. And then we're going to take a compass again for both the center point B and the center point C, and then take those 2 points to be the outside points or the points on the circle. And then we take the intersection of those 2 circles and get DE. And then we take a straight edge and we draw a line DE through the point A. And then we're going to go ahead and take, so you can do the next one now, the point F, which is the intersection of the line and the circle. And that would be the first point of our pentagon. So then we're going to use a compass again to draw the center point circle, the center point of the circle C and a point A on the circle. And that will also give us the intersection of the red circle with the circle with center point C, which is G and H, which we'll use a straight edge to draw that line from G to H. And then we get a point I. And then from here, we're going to take a compass again and take the circle with center point I and then a point F on the circle. And then that would give us a point that's going to lie right there, which is J. So the circle, the intersection of the circle and a line AB, which gives us J. And then from there.
Or I want to note that
go ahead.
This length from F to J is going to be the length of all our line segments for the regular pentagon. So now we're going to construct a circle with F being the center of the circle and J being a point on the circle.
Yes. And also this is like technically arbitrary. distance because if we were to scale this smaller or larger, the distance would still be between the point or the point F to J.
Mhm.
So we just define that that point or that distance from F to J will be that defined distance for our pentagon. And so no matter how we scale it up or down, it's defined to just be that distance F to J.
Yeah. So then we're going to construct that circle with F being the center, J being the point on the circle. And since this is the length of our line segments of our pentagon, then we know that the intersection between the circle with F being the center and our original red circle are going to be points for our pentagon.
Yes.
So then we get the points K and L, which are going to be the first 3 points of our pentagon. And then using the fact that um, they are the same. So we know that F and K, F and L are the same line are the same length. So we're going to make this be the radius of our circles. And since the radius of the circles are all equivalent, then we're going to use that to find our new points on the circle on the red circle.
Yes. So like for example, we know FK is the radius that's equal to FL. And so if we took a circle with K as the center point and the radius being KF, we can go ahead and take this next point, which is M, and we know that KM will be equal to KF, which is equal to FL. And we do the same process again with the center point being M now, and now we have a new point N. And we say that MN is equal to MK, and then all of that follows again.
Yes. And then just to check, we're gonna take N, the circle where N is the center and M is a point on there. And we also see that L is also a point on that circle. So we know that all these side links are gonna be the same length as the radius of these circles.
Yes, sir.
So then we get our regular pentagon. So let's connect the line segments.
Using a straight edge.
And then now from this construction, we get that the angles 108, which is equivalent to
3 pi over 5.
is a constructible angle. And then we can also take these isosceles triangles because since A is the center of the circle and F, L, N, and M are all points on the circle, we know that the distance between the center of the center point of the circle and those points on the circle are gonna have the radius length.
Yeah.
So we have that all these triangles are isosceles.
And so we have base angles. Well, we first have the angle 72, which is 2 pi over 5, but then we also have the base angle 54, and 54 is equivalent to 3 pi over 10.
And then another cool thing about this construction is if we take the perpendicular bisector of each line segment and we find the point the point of intersection between those perpendicular bisectors and our red circle, then we can create a tangent.
Yeah.
So first we're going to take this perpendicular bisector by what we showed earlier in the video, the exact same way we did. And then we're just going to take the perpendicular bisector of each line segment. And then as we can see, these are the points of intersection.
Yes.
So then after we take all these points, we can create a regular tangent. So we'll get, this is what our regular tangent will look like. And then we get that the angle 144 degrees is constructible, which is equivalent to 4 pi over 5. So we get that angle is constructible. And then again, if we create these isosceles triangles, then we also get that the angle 72 degrees is constructible, which we already showed.
5, yeah.
Yeah. And then we also get that the angle 36 degrees is constructible, which is
pi over 5.
Pi over 5. So yeah, this is a cool construction that we thought would be interesting to show. This works for many polygon or regular polygon constructions, and you can always find new angles that are constructible.
Yeah, like for an example, like if we found a way to construct a square using a straight edge and compass, we can do the same process where we take the perpendicular bisector of each line segment of that square and we get a octagon.
Mhm.
And then you could do that again and get a
Get a
16
16
gon.
yeah.
So interesting.
So now we're gonna go back to our presentation and show you our references. So we didn't plagiarize.
Yes, sir.
All right, that's the end of the video. Thank you guys for watching.